Bismillahirrahmanirrahim. Assalamu alaikum students. We are here again with the part B of lecture number 4. So let's start what we were discussing in the last slide. We were discussing the stall on pipeline, effects of stall on pipeline. So as we had discussed that whenever some instruction gets stuck in some stage, so no new instruction can enter in the previous stage, and if that instruction doesn't execute or complete its job in one clock cycle, in the next clock cycle again this bubble starts to move forward. All this hyphen signs where I am moving my cursor, this yellow ball, so you can see that bubble passes through the pipeline. So this hyphen sign or the dash is called the bubble in the execution pipeline. So now let's discuss that actions that cause a pipeline stall. That what are the causes? How does this stall comes in the execution? So the first step is the first point is the excess external storage. So as a rule of thumb, you must be knowing that all the external storage are very slow as compared to the processor internal registers. As a rule of thumb, you can say that the RAM is slower than the internal storage of processor, and the hard drive is slower than the RAM, and the external hard drive is more slower than the internal hard drive. So and in the same manner this happens. So if we are fetching our operands from the external storage, then obviously the stall pipeline will experience a stall. This was the first reason, and the second reason is invoking a coprocessor. As we had discussed this in the chapter number 4, that processor has to play a role of a coprocessor also, and the coprocessor always works under the supervision of the main processor. So when a coprocessor is invoked, in that case the role of the main processor is to understand the command type, that either it is a arithmetic command or the logical command or the word processing command, and then it passes or it invokes the appropriate coprocessor. So in this a stall comes, and third one is the branch to a new location. Whenever the program jumps to a new location, the decision box comes in the processing, and upon the decision computer has to jump to some branch, then the stall also occurs, and whenever we call a subroutine. So these are the causes due to which the stall occurs in the execution pipeline. At achieving maximum, how we can achieve maximum speed? Obviously program must be written to accommodate instruction pipeline. Programs must be written to accommodate instruction pipeline. It means that our operands must be coming from the internal registers. It will give us a boost, and but if we are copying our data from the external drives, then obviously stall will come. So this is the first point. And to minimize stall, avoid introducing unnecessary branches. So if your program is straightforward and there is no significant impact of a branch, then don't make the unnecessary branches in the programming, because whenever it jumps to a branch, then a stall comes. And what are the branches? Okay, if I tell you that for example, take our everyday industry experience, because all these computers are used in industry very widely, and they control the devices, through microcontrollers and through microprocessor, through PLCs, through distributed control system. So all these things are widely used in everyday industry. So, for example, in a process industry, we are making cement or fertilizer or milk or processing water or whatever. So, if several factors need to be checked and need to be in the safe limits. For example, if I'm making the fertilizer and I don't control the pressure or the volume or some catalyst, then there is a fear of all the product will go in vain. It will not be usable for anyone, and it will have to be discarded or will become the garbage. So these factors needs immediate attention, which are very critical to the product. So they need the very urgent attention. So I will declare them. I will declare them all of these parameters as the interrupt in the start of my program that execute this program. But if any interrupt signal it goes beyond its limits or it approaches to its limit, then immediately stop the main program and first try to keep that try to make that interrupt signal within its acceptable limits, with its optimum limits, and then again execute the program from the same point where the program was suspended. So such arrangement are called branches or the subroutines. So interchangeably they are used. You can say them synonym to each other. So so we need to avoid introducing unnecessary branches wherever possible. But in the process industry, so we cannot avoid it. So you can say that this is applicable for a test bed, which we can create in a lab. Because in that we can demonstrate that when the branches are there, unnecessary branches are there, so many branches are there, and the program computes and jumps towards that branches, then the stall comes, and when the number of branches becomes less in number, so the stall also reduces. So, and the other thing is delay references to result registers. Delay references to result registers. For example, if the results are referenced to or being taken slowly, so the registers having the result will not become emptied, and this may also cause the stall. So we need to avoid all these parameters if we want to get rid of stall, but completely it is not possible. And the other mechanism which we use to minimize the stall is, example of avoiding stall is carefully see this code written at A position. You can see that the first instruction is saying that add A and B and save the result in C, and then in the second instruction we are asking the system to subtract C from the content of E and save the result. Okay, save the result, but this star showing that stalls eliminated by rearranging A to B. Means stall means here the star means the stall is coming, because once C is computed, C is not computed, we cannot get the result of second instruction. And now see the third instruction, it is saying that add G and H and save the result on F. The similar condition again happening, that the result of instruction 3 is becoming the operand for instruction 4, where we are saying that subtract the content of F from content of I and save the result in register J. Similarly, on the fifth line of this code, we are saying that add k, the content of the register k into L, and then save the result on the register M. And in the successive instruction, that is the instruction number 6, we are again saying that subtract contents of register N from register M. So if M will not be computed, we cannot subtract the contents of N from M and save the result on P. Now see, and now concentrate on the part B of the same code. See, the first command is as it is, and we have replaced the place of second command, and we have brought it instead of in the second place, we have brought it down to the fourth place. So we have actually rearranged the code, and the instruction coming in the as a third instruction in the code A is coming on the second instruction in code B, and similarly the instruction coming on the number fifth instruction, this in the code A has been rearranged at the instruction number 3. So what we got from this rearrangement is basically we got 2 clock cycles time, because C is to be calculated in stage 5, so we will be having 2 clock cycles, so that if there is a delay in the calculation of C, so it will be there must be sufficient delay available in the code, so that when the fourth instruction will come, so we can fairly say that C would have been calculated, so there would no stall coming in, and similarly the second instruction's result is being used in the instruction number 5, so it has also a delay of 2 clock cycles, so it will be sufficiently computed, and so on. In the third instruction, the result M will be calculated and will be computed, and after 2 clock cycles in the sixth instruction, when it will be required to subtract the content of N from it, it will be readily available. So in this way we avoided stall by the rearrangement of code. But remember this, that this can happen only in the labs, whenever we are dealing in the process industry. We are making some physical product like cement or milk or some spices or flour or whatever. So we cannot change the order. Like if you cook some food and you change the order, then you cannot have a good and delicious dish ready at the end. But if you follow all the steps as it is expected, then you will get a good dish. Similarly, this rearrangement of code is not always possible. It is possible wherever you are writing some codes which doesn't relates to some process industry or some physical product. So there is a room available for the rearrangement. Okay, but if some process, it is being used in some process industry where we cannot break the order, then remember that you cannot rearrange it always. Okay, I think you got the point, and now move forward. A note about pipeline: although hardware that uses an instruction pipeline will not run a full speed unless programs are written to accommodate the pipeline, a programmer can choose to ignore pipelining and assume the hardware will automatically increase speed whenever possible. So mainly in the hardware, mostly the computers are the hardware is that much sophisticated nowadays that it takes care of it himself, and doesn't require a code for it. So programmer can sometimes it can ignore it because the hardware will be taking care of it automatically, and but its structure and its causes, they are necessary for him to understand, to write it in a better way wherever possible. And wherever as we said that stall cannot be fully eliminated because it is inheritedly present in the nature of few opcodes, because their operands might be larger or so complex, or maybe they are located in some external memory, or worse than that, they can be coming from some real system, which would be more time consuming than the external memory. But these are the limitations. Remember, we are living in a real world. We are not in the paradise. Our all wishes cannot be fulfilled in this world. So we have to live with these systems, and they need to be they need to be improved, and constantly works are underway to improve the system. But still, all the wishes of humans, they can be fulfilled in the paradise. In the world, there are so many if and buts, and so many physical constraints, and such things which we cannot eliminate. So so wherever we cannot completely eliminate the stall, like in the process industry, so then what we do is that we document it, have no effect on no op. We document it with the no op instruction, and this no op instruction doesn't have any effect on the registers, memory, program counter, or computations, and can be inserted to avoid instruction stalls. What does this mean, no op instruction? Often used by a compiler. That whenever compilers watches this, that or feels that here stall might come, so what it will do, that it will slow down the program's speed by itself, so that it might minimize the stall, and by introducing the no op instructions in the code. So compiler automatically do this, and we don't need to do this. So this is to document the stall. Use of no op example, you can see that instruction K is saying add A and B and save the result on C, and because you can see that compiler is so intelligent that it has seen that the result of previous instruction is becoming the operand of the next instruction. So it has sensed it that there might be some problem in calculating the C. So what does it do? That it introduces a no op instruction at instruction L plus 1, and then K plus 2 is computed after one clock cycle. So in this way, no op allows time for results from register C to be fetched for subtract operation. So it gives the time so that there must be no stall, or system must not be overwhelmed with the bombardment of the instructions. And another way to minimize the stall is the forwarding. And let's discuss it, that what the forwarding means. That hardware optimization to avoid a stall. How does we optimize the hardware? It allows ALU to reference result in next instruction. Example instruction, again the same instruction, that add A and B and save the result on C, and instruction K plus 1 says that subtract the content of C from E, and this is the instruction K plus 1. So forwarding hardware passes result of add operation directly to ALU for the next instruction. It means that if we deploy the technique of forwarding, then it will be having such a that there is no need to introduce the no op instruction, because our processor in this case uh, would be intelligent enough that it will not send the result of C to the external drive. It will keep a local copy of C readily available for the next instruction. So this technique is called forwarding. I hope that you understood it. If not, so you can read it from the book, and even if in reading from the book you don't understand it, so you can ask it in the interactive session. So next article is the types of operations. Types of operation includes the operations usually classified into groups. An example categorization is arithmetic instructions, which involves the integer arithmetic, logical instructions that are also called the Boolean instructions, data access and transfer instructions. This is the same role which microsequencer does, that it accesses the data from somewhere, from some external drive or some place, and then puts it on the buses, and make sure that it is received on the other side register. So and similarly in the opposite direction, it fetches the results from the registers and then put them on the buses, and saves it at the specified location. So data access and transfer instructions, and the conditional and unconditional branch instructions. These branches I have told you in the same lecture, so you can listen it again if you rewind this lecture, and again listen that what I told you about branches. That whenever some parameter goes out, or that some decision box comes, and upon the value of the decision box, out of two branches, out of two paths, it has to take one path, that is called a branch. And conditional and unconditional, this is a new thing, because for example, if we need to take the branch on the decision of a decision box, or some already referenced value, then it is called the conditional branch. That if this condition matches, then this will happen. But in some cases, we can run the program. We can run the program in unconditional way, that when we can tell the program that when you come on the instruction number 15, then unconditionally jump to instruction number 60 or 55, and then after running in the sequence from 55 to 75, then again jump back to instruction number 20 or whatever. So because in that case it will not look for any reference value or some decision box, because we have unconditionally told him to jump at some time. So these are the conditional and unconditional branch instructions. And the next one is the floating point instructions. So floating point instructions, it includes the instructions which are dealing with the floating point values, or the scientific values which we come across in physics, mathematics, or in any other subject which has a very precise readings, or the floating point readings. So whenever we are dealing with the floating point values, so floating point instructions are called to deal with them. And the last one is the processor control instruction. So processor control, this is so much complex that it needs to be there are the control instructions which the processor uses for its own internal operations, and that sixth category is the processor control instruction. So now in this lecture we have discussed different things. We discussed the reasons of the stall, and the minimization or elimination techniques of stalls, and the types of operands. So I hope that you enjoyed this lecture and fully understood that what we discussed. And if there is any problem in any part of this lecture or any lecture, so you can ask me in the interactive session. But before putting some question in the interactive session, I would suggest that if you don't understand it once, listen it again, and also consult your book, because all this is available in the written form in your book. And even if you don't understand, then don't hesitate to ask. I'm ready there. I'm available there to assist you, to tell you that any question you put, you will get the answers. And happy learning, and Allah Hafiz. Meet you in the next class. Assalamu alaikum.